have some other DCI examples here, but I will skip those. Again, this is an answer to some of the questions that people sent in, or the suggestions that people sent in about what I should talk about.
今日話そうとしたこと内容の話の、質問があったんですけど、この話をしようと。
So we've talked about what the system is and what the system does. And what I mean by architecture here is closely related to what the system is.
そのシステムは何かっていう話が、このアーキテクチャで話そうとしているんですね。
Most domain knowledge isn't in algorithms. It's in what are the parts of the system. And so the what the system is view is particularly useful view, more so than what the system does.
アルゴリズムとかそっちの話ではない。
Algorithms are in parts.
So if I'm building a software system, the key to success in a software system isn't your knowledge of programming language.
ビジネスの成功はプログラムの言語の知識じゃないんですよね。
4 years ago, I did not know any Java. And I put up an environment on GitHub, and I decided I wanted everyone to be able to download it. So it's implemented in Java. So I took 2 days and I learned Java. I mean, that is not the hard part.
プログラミングの話じゃない。2日で学べるようなそういう話じゃないんですよね、実際。
The hard part is understanding the domain, the business.
必要なことはドメインを学ぶ。
Most of that knowledge is structural. It's not algorithms. There are some exceptions. I mean, if I'm
例外もあるけど、構造的なことを、アーキテクチャとしては理解をする。
アーキテクチャはアルゴリズムの中にあるのではないと。
例外はある。構造にある。
So there are exceptions like network routing. A lot of the domain knowledge there is algorithm, or intercepting a ballistic missile. This close to Korea, maybe you ought to be investigating that. It's really worrisome.
Yeah.
But most of it is structural. What are the building blocks? Now, of course, what I just said is bullshit.
今言ったことは間違えてる。
全然ダメだ。ブルーシットだ。
ブルーシット。
Because
かもしれない。
it presumes that structure is one thing and time is something completely different. Is that true?
Again.
Structure what?
Structure is one thing. I can define it. And time, or algorithm, or sequencing is something else. Totally unrelated.
You mean the sequence of
Right.
processing?
Is that true? I mean, in physics, we have X, Y, Z, and T. T is orthogonal to X, Y, and Z. Is time independent of space?
時間と空間によって全ての解が違う。
時間と空間は別ですかって言ったらそうじゃないでしょ。それは一緒でしょっていう感じ。
ああ、なるほどなるほど。
So, I think this is a fiction. And in understanding commonality and variation, I want to build an argument that kind of destroys that fiction, and it addresses some of the questions that I got, and then it goes further. This is going to go uphill very fast.
ちょっと整理しますけど、まずそもそも、今2つ概念出してるものは、ストラクチャーと、あとはtime of space その or time of sequences are different is your organization. そうストラクチャーっていうものと、シーケンスの時間とかそのスペースっていうものが、完璧に切り離されるものですかっていう話を接触しないでおいて、さっき高木さんの補足があったように、それはノーですね。っていうふうに、リーンアーキテクチャの話かな、DCI とかっていうもので、今回は今日はそのフィクションを、壊そうとしてる。
ストラクチャーって空間的なものを捉えてて、でアルゴリズムってこう手順だから時間的なものっていうふうに捉えていらっしゃるんですよね。それが本当に別だけどそうじゃないでしょっていう。それは別だけどフィクションだから、時間空間別だけどフィクションだから、それを壊そうとしてるっていうことですね。
なるほどなるほど、そういう意味。わかりました。
So there's this book called Lean Architecture, and that Gertrud and I wrote, and it has both parts in it, both what the system is and what the system does. And traditionally, I'm the what the system is guy, and Gertrud is the what the system does woman. She's the use case person, I'm the class guy.
リーンアーキテクチャの話で、What System Is と What System 両方あるんだけど、2人で共著ということになっています。で、クラスガイとユースケースというのが。
What I want to focus on, to start focusing on tonight, is more the structure part, because I think that's what people have been struggling with. And they're asking about things like the multi-paradigm design book, and that's closely related to what the system is. Now, I've already talked about using multiple paradigms, and these are the classic programming paradigms of classes and functions and templates and state machines and things like that.
今日話すのはストラクチャーの方の話をメインに扱う。
Yeah. Usually, in a very practical sense, if I'm building a system, I start with that because that tends to be stable over time. And so I can leave that alone, and then I can focus on building the features. Those are what people ask for, and they tend to be use cases. That's what we sell. We don't sell classes, we sell use cases.
我々が売ってるのはクラスを売ってるんです。ユースケースを売って、ビジネスをしている。
However, it's really twisted. And you can't cleanly separate these. Now, in the Lean Architecture book, we pretend that we can. So, if we go back 50 years, people really didn't care about structure. It was all about von Neumann machine, which was a mathematical model of progression of state in time. And we had languages like Fortran and Pascal, and no one really paid attention to the data structure.
50年前の話でノーマンコンピューターとかその辺の話をしたんですけど、実際このリーンアーキテクチャの本ではその複雑性に対して対応することができるって言ってるけど難しい実際は。もう50年前は実はもうちょっと実現したいことが簡単っていうかもうできる少なかったから。
So if you looked at the first machines or the first operating systems, for you old guys in the audience, what was the expensive part of the machine that you had to optimize? It was the CPU. The whole focus was on what the system does. And the programming languages like Fortran and Pascal served that.
最初は CPU に要はお金が一番かかるとか、要はトランザクションが一番早く行われるっていうところが最初にお金を使うところで、そこでフォートランとかその辺がなんだろうな、パフォーマンスに影響できるところ、そこを最初注力をした最初は。
その CPU に集中するといったら、その What System Does というシステムが何をするかっていうことに集中していて、What System Is システムのホームってところにはあんまりお金をかけない。で、フォートランみたいな言語ってはその延長、What System Does の延長で作られているという、こういうことです。
Yeah, and part of the point is back in the 1960s and 1970s, nobody was making this distinction because it was all focusing on one thing, which is what the system does.
その当時はそんなに考えなかったその違いを。
Then in the 1970s, what happened?
1970何が
Databases.
データベースができた。
And all of a sudden, the bottleneck was rapid access of data. Yeah, Peter Code. And everyone forgot about the CPU and what the system does, and now it was SQL. And everything was about what the system is. And this followed computer architecture and technology.
1970年代その時に包括システムイーツが重要になっていた。
Then came the 1980s.
多分、You mean the invention of relational database?
Yeah. But it was more a business need.
I see. Yeah.
Businesses were discovering that they could use databases to manage finance and manage business and.
Okay, so invention of database is reflecting such the needs. Yeah. 1970年代になってデータベースという形でWhat System Is というのが具体的注意の関心の的になってきたっていうことだったものがね。だから彼の言ってるWhat System Is っていうのはかなりそのデータモデルに近い。データモデルに近い。
And COD and DATE, that was the birth and death of computer science. It's about the only computer science that's really science that's ever been done.
COD and DATE.
Yeah, it's relational theory. It's real science. I mean, everything else is just fake science. So that was real science. We haven't done any real science since.
本当にサイエンスっていうのはコプさんの記録だけでしょ。
コプさんはデートさん。
Yeah. Then the 1980s came. What was that?
何が起きた？
Networks of computers.
コンピューターネットワーク。
And so now we don't have Fortran, we don't have SQL, what do we have? Small talk. And so we have networks of objects communicating with each other. So if we look at history, there's been this cycle back and forth between what the system is and what the system does.
80年代やってスピードトークがあって、What System Is と Does がどんどん徐々に変わって、互いに変わっていくの時代が進んでいくと。
It's always been at one extreme or the other. Now, if I look at the architecture of this room here, or of the room, how do you pronounce it? Room. Of the space here. I can talk about the walls and the floors, and that's what the space is. Why is it that way? Or what did you notice about that space? It affected where you had to walk, how you entered. It affected the process of what you did. So there's this interplay, this kind of yin-yang between what the system is and what the system does. And this is something that the West still does not understand. There's another dichotomy which is commonality and variation. So we presume that they are separate. Every once in a while, we get embarrassed. So in Artificial Intelligence magazine, where's my AI guy? Okay. Did you read AI magazine, winter of 1986? At the end.
I was 10 years old.
So, an article by Ron Brockman. I was working for Ron at the time, and it was based on an old elephant joke. You know elephant jokes?
オールドエレファントジョーク1986年
How do you put an elephant in a Volkswagen?
Yeah. Just open the door.
You open the door and put the elephant in. How do you put a giraffe in a Volkswagen?
キリンをどうやって入れるか
Just take out the elephant parts.
See, this is a memory test.
よう覚えてる
覚えてるかどうかのテストだけど。
So there are these stupid elephant jokes. So what's large, gray, lives in trees, and has a trunk? An elephant. I lied about the trees. And there was an article in AI magazine, winter of 1986, by Ron Brockman called I Lied About the Trees, or Defaults and Cancellation in Knowledge Representation. And it was about knowledge taxonomies where there would be a commonality and then an exception.
So you mean the elephant is not actually in the trees?
I lied about the trees.
Yeah.
So I will define the answer as being large, gray, has a trunk, and lives in trees, except it doesn't live in trees.
エレファントジョーク、その象のジョークで大きくて、灰色で花を持ってて、で森の中にいるのはなんだってこういうジョークなんですね。で答えでそれは象ですと。ただ私はその森の中にいるってことについては嘘を言いましたってこれは答えなんです。答えなんです。だけどその森の中に象は森の中にいないからそれは正しいんだけど、その質問されたことに対して嘘をついていいんであれば何でも答えられるよねっていうこういう話なんですね。
Now, let's go back to our old friend list. And we'll do this in C++. It's a template of class T, class list, and what will be the representation? So I will have something called struct cell T star element cell star next star head. So this is what a linked list might look like in C++. And so I have the list object. It has a field in it called head, which points to something of type cell that points to the actual object and then points to the next cell. So that's what a linked list looks like. So how many bytes is a list of 1,000,000 integers? A lot. I can represent a list of integers much more compactly, because I can just have a list of integers be represented as a vector. Whoa. What's that stuff?
Excited.
And she has a heart attack. What do I do in C++? I say template, class list of int star Beck. So when the compiler sees any list, it will use this template. Unless I lie about the trees.
Yeah. This is a lie.
This is a lie. This is a list, except it doesn't look like that. Commonality. Here, most of the variation is in T. But and if I change T, all of this commonality is still true. Here, the commonality is no longer true. It's a different data structure. And you anticipated this earlier when you said, well, maybe the data structure is different. So here, we have a special kind of variation, and this is called negative variation, because it violates the commonality. Now, why is this important? Because symmetry, which is what this is, perfectly separates commonality and variation. It's a perfect symmetry. Now, let's go back to the Big Bang. What? Something went wrong at the Big Bang. At the Big Bang, there was an equal amount of matter and antimatter. And something went wrong, all the antimatter went away somewhere, and what we're left with is matter. The only reason that matter exists is because there is no symmetry in the universe. And you can prove it. Physicists can prove this. There is no pure symmetry.
ビッグバンの話ですよね、今の話は。
対称性の破れの話。
最初に物があってみたいな話。
物質があったらアンチマター、反物質もあるはずだけど、アンチマターないので、なのでシンメトリー成り立ってないんです。
So, you're a programmer. You're modeling nature. Everything you're modeling has been created. You are using a symmetric programming language that has commonality and variation. An elegant, symmetric programming language. Like, I'll pick on you, like Lisp. Or Smalltalk. And you're modeling something that has no symmetry. So it doesn't quite fit. This adds accidental complexity.
So this is accidental, you know.
This is how I express that weirdness.
Oh, yeah.
So C++ can capture some of the symmetry breaking.
In the case of dealing with integer, this structure is appropriate. But it's breaking symmetry, you mean.
Yeah, it breaks the symmetry
Yeah.
of this. All processes in nature are processes of symmetry breaking. And this is something we don't anticipate. Let's say I have a pool of milk. Infinite in scope, perfectly symmetric. And I drop a drop of milk into this to make a splash. Now, there's a law in physics called Curie's law that says any symmetry of the effect is a symmetry of the cause. What does the result look like?
原因がその対照的であれば、結果も対照的になるべきだっていうことを、ミルクをほとんどこうしたとしたら、この時のしぶきっていうのは対照形になるはずだということをこう言ってはるんですけど。
What does the result look like? Well, it's a crown. Do you know this crown always has a multiple of exactly 12 droplets? Yes. And it's just simple physics. You can do the dynamic force equations for this, and it must be a multiple of 12. It just falls out of the calculation. It has nothing to do with the molecular structure of milk. It has, and for any viscous fluid. Now, this is weird. So, I mean, God is kind of laughing at us from within this pool of milk as we're trying to figure out what's going on. Just as God is laughing at us as we try to take our symmetric design knife and cover up and carve out broken symmetries from the analysis space. So, the multi-paradigm design stuff starts with this simple model of pure symmetry. Now, why do we start there? Why do we care? Why is this useful? Because your brain is pretty dumb. Your brain likes to save energy. So, when I remember your face, remembering this meeting, I will only remember half of it. Because my brain knows that when nature creates things, they're approximately symmetric. And that all I need to remember is half of him. It's good enough. So if I am a monkey and I just remember half of a tiger, that's enough to protect me. I don't have to remember that its hair was parted exactly like this, right? And so our minds love perfect symmetry, even though nature isn't built that way. And so,
It's economic.
It's economy. Yeah, it saves energy. I mean, the brain uses, what, 40 watts of power? And anything it can do to reduce the energy and stay cool is energy well spent.
人をこう理解するときに半分理解すればあとの半分はなんとなく想像ができるちょっとチートするって感じですね頭が
物事は対照的だろうが人間にとっては節約できると認知能力で節約できるから物事を我々は対照的なものであるとして理解したがるとだから現実の物事はそうではないという、
So,
in this case, this template is symmetric.
yes,
So,
yes.
But in the case of integer, it is more efficient. So, sometimes we have to choose this asymmetric solution.
Yeah? Yeah. It's more efficient. I mean, this will work for integers.
Yeah.
It's just not efficient.
Yeah.
Here we're saving energy. It's economy. Now nature is always trying to save energy. Third law of thermodynamics. More or less. It isn't quite true. Because there is real self-organization in the universe. So the third law of thermodynamics isn't quite true. But close enough. But again, if we look beyond symmetry, even the third law of thermodynamics breaks. Otherwise, matter would be evenly distributed throughout the universe. But it tended to come together in irregular galaxies and things like this. So there is self-organization. The universe is alive.
マルチバース。
I mean, if you think about this, when an egg becomes fertilized by a sperm, then it divides into 2 cells, and then 4. It's perfectly symmetric, right? And then 8, and then 16, and then it gets a head. Where in the hell did that come from? The symmetry spontaneously breaks.
卵で細胞分裂するときに1個は2つに分かれても2つが4つに分かれても全部シンメトリックだと同じだけどある時突然にそこから頭が出たりする頭っていうのはシンメトリーがブレイク対称性が来ないと出てこない自然はもともとそういうもんなんだとで我々のソフトウェアもそうなんだと言ってるんじゃないかと思います。
Now, things get even more interesting because this gets into the realm of time. So, who here understands state, like in state machine?
状態について理解してる。
You know you cannot understand state without understanding time. It makes no sense to discuss state unless you discuss change of state. Something that just stays in one state is really boring. I mean, there's no need to discuss state. I can just discuss structure. So space and time are interrelated. Now, where does function come from? Why did you walk the way you walked? Think of your house. The architect of your house or your apartment made it a certain way. Think of waking up in the morning and getting out of bed. What's the first thing you do?
朝起きたらまず何やるのかっていうことを。ああ。Open the curtain.
I mean, maybe you go and brush your teeth. Maybe you take a shower. Maybe you kiss your wife good morning. Maybe you get a cup of tea. So I can look at the footsteps around your house. The reason architects carve out space is for the sake of the patterns of events. Now, if you read Alexander,
パターンのためにアーキテクトっていうのは家の構造を作るんですね。イベントのパターン。
most people in the pattern community think that what Alexander is talking about is patterns of space, carving out space. And I believed that for 10 years. And then Richard Gabriel and I were talking about it, and I said, well, I wonder if Alexander really understands time. And he said, go back and read it again. He has a whole chapter on patterns of events. What Alexander is about is using space to shape the patterns of events, the form of function.
昨日の前にパターン、昨日の前にそのパターンのことを話している。アレクザンダー。
アレクサンダーってなんかそのパターンランゲージについて
建築の
アレクサンダーがパターンを書いてそのパターンっていうのはその建物の配置とかそういうことをストラクチャーに書いてついての本なんですけどもそこでアレクサンダーが語っているのはイベントのパターンイベントのパターンこういうふうに物事が動いていくっていうパターンを元にして建物のストラクチャーについてのパターンを語っているとだからそのストラクチャーっていうのはスタティックな静的なものなんだけども実はそれはその時間的なものを反映して作ってできているというようなことを
Now, I'll come back to this in a second, which will be my last statement. But there was one more question that someone asked about, which was, what is the relationship between Lean Architecture and DDD?
DDD アバウトコードで書いてます。
There is no analysis in DDD.
分析やな。
I mean, Eric Evans, he says that explicitly in the book. There is no analysis. We go directly from concept to code.
エヴァンス自体もないっていうふうに言っている。
Lean architecture is about people and their mental models. And so we socialize, we discuss what our shared models are. And it's not just one programmer taking their model and putting it into the code. It's a social event. To support that social event, we need a language or a formalism or a notation or some way of communicating what we are talking about. And it usually is not the programming language, because the programming language cannot express these things.
リーンアーキテクチャっていうのはプログラミング言語とは別に、例えばディスカッションであったりとか、その関係ないプログラミング言語とはまた別の話である。もうソーシャルな活動である。
So Eric Evans throws all of that away.
まあ、エヴァンスはこのことは言ってない。
There's no social communication because there's no analysis. There is no place for the conversation about form, only structure.
ストラクチャーのことしか、まあ、その中では議論はされてなくて、フォームのことは全く議論はしてない。
So, Lean architecture starts with form. It's kind of abstract to concrete. So we start with the commonalities and variations, both in time and in space, and then we will select the right tool to implement what we want to talk about. Whereas DDD is about code. No analysis, no form, no socialization of form. Alexander makes it very clear that architecture is a social activity and that you bring the community together to agree about what the pattern language is. You do not have an architect on an ivory tower who just goes directly to code. So it starts concrete. And what is easier? I mean, I can't remember who this was. If it was Mies van der Rohe, that says that the two most important tools of the architect are the eraser in the drafting room and the sledgehammer on the construction site. But it's a lot easier to use an eraser.
設計の場面で消しゴムを使う方がその建築の現場でこういう紙ずして持って作ったものを叩き潰すよりだいぶ楽だよねっていう。
So analysis allows us to be agile, to get feedback, to do experiments. If I've reduced it to code, it's like concrete and it sets very fast and it's very inflexible because I have committed to something concrete.
Sometimes you can use the source code to express your idea about the abstract things.
You can, but our languages are so impoverished that you're usually better off in English. And I mean, Gertrud can talk a long time about this in UML, and I'm sure you get questions about, okay, what is exactly the right format of a use case, or that UML will say for a design, exactly, and especially for use cases. Exactly what is the right format? And it's like, who gives a damn?
The tool.
It's a tool. So, and if I write it down, that's one direction communication. If I'm talking with you, there's feedback. So, using language, including the unified modeling language, is a one-direction form of communication that presumes that I know everything. If I'm talking, I get the feedback. So someone wanted me to go into this DVD thing, but let me end with just kind of a review of where we have been. So we started with just what is called CVS, commonality, variation. I think the S stands for synthesis. Pure symmetry. We also separated space and time as being two different things. Then we introduced negative variation. Which is kind of a way of cheating for getting some broken symmetry into the system. And we started talking about a relationship between time and space. And as I said, both of these are bullshit. So software is a very young field, and most of the areas where we are exploring software are very young. If you are building a building, you're building on thousands of years of insight. If you have thousands of years to look at a building, you start to understand how time and space are not separate. And you can communicate them in a single formalism that combines time and space together, as well as accommodating all of the broken symmetries. And these are called patterns. So what multi-paradigm design is, it's mainly this, because that's a good fit for our symmetric brains, with enough of this to be able to accommodate complexity. This is where complexity comes from, is in the broken symmetry, the negative variation. This is a simple system. Someday, I want to sit down with Dave Snowden. I almost said Ed Snowden. I guess that joke doesn't work here. Sit down with Dave Snowden, who has the Knafen framework of complexity, simple, complicated, complex, and chaotic. And his whole framework is in terms of time. I think you can make a complexity framework that's only in terms of structure, and that has to do with symmetry and the degree of broken symmetry in it, without introducing time. But a failure to recognize broken symmetry is what causes accidental complexity in architecture, because it's a bad fit. If I can program in theory, I'm not even sure what this means, program in patterns, this accommodates the commonalities and variabilities as well as the time element. It integrates what the system is, patterns of space, with what the system does, patterns of events. And Alexander is clearly thinking of patterns in this way, that they are both space and time together. He was very much influenced by his time here in working with the Japanese. And how many of you have been to Aishingakuen?
アレクザンダーが設計した学校ですよね。
He designed it.
Yeah.
It's what, 40 kilometers from here? Or?
場所と
パターンっていうのは、そのフレームワークと同じ意味で使ってる。
パターンが出るパターン。
How many of you know Nakano Sensei? You don't know Nakano Sensei? Oh, you've got to get Nakano Sensei to this group. Do you know this guy? So he is the head for the Center for Environmental Structure, Alexander's company, here in Japan. And he does a lot of work. Yeah, he does a lot of work with the software community.
アレクサンダー
Many of us would know Alexander. Yeah, Christopher Alexander.
Yeah.
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 He designed some school in Japan, the Aishin Gakuen.
Yes, Alexander did.
ああ、愛心があって、ああ、
And one of the people who was working with him was Nakano sensei.
中野先生っていう方が日本でアレクサンダーと一緒に
I think it's Hiroshi Nakano.
広島さん
I think so. He's a really funny guy. He wears a little French beret. He's kind of kind of fat and short. He's kind of like an elf with this beret and a little goatee. He's really a funny guy. Great guy. And I think he knows a lot about what the software community is trying to do. So,
So you mean the commonality and variability is the very rational and easy to understand, but too simple. So this simplicity breaks anywhere, and you should have your negative inheritance.
right?
Yeah, and if you accumulate such experience, you get to the patterns.
Right. I mean, this you can even do with artificial intelligence.
What is it?
Right?
新メ
Whatever that means.
Yeah.
うん
だから共通性と可変性に戻す分析って先ほど枠にしたかったら、ある程度その場所までできていくと、ある意味簡単になると。
簡単にできると。
だけど、それやってると、さっきのリストのケースみたいに、どうしてもそのシンメトリーを破らないと解決できないことができてきます。で、そういうのを何回も繰り返していくと、人類はその進化パターンというのに到達すると。
真ん中は何ですか？バリエーションというか。
それはネガティブ
Variation.
バリエーション。
さっきのリストみたいに、あるケース、ほとんどのケースでは、リンクドリスト、ノードをこうつなげていくという形式がいいんだけれども、整数の場合にはそうじゃなく単にこうベクトル整数
やるだけでいいと。
それを彼はシンメトリーの対称性の役割だと言っている。で、どうしても設計上そういうのを破らなくちゃいけない場面が出てくると。そういうことを繰り返していくと、どういう時にどういうことをすればいいのかというパターンができると。それは時間が蓄積されていく。
So this comes mainly from the right brain and from separating the right and left brain. This comes from a combination of left brain and right brain. And this comes from the hara. The center. Yourself, your essence. So this is somewhat purely rational. I mean, if I take this further, the next step beyond this is pure Fortran or pure SQL, which only is looking at half of the problem. At least these are all looking at both time and space, both commonality and variation. Only this one integrates them into a single whole. So multi-paradigm design and the structural part of lean architecture are different points on this continuum of time and space.
So in the left hand, you separate time and space clearly.
Yes.
But it doesn't work well in some cases. It's a middle case. And in patterns, you do not distinguish time and space. It's somewhat they are mixed together. Where, yeah.
And then beyond patterns, there's the theory of centers. And beyond centers, there's the concept of the one, or the I, or mume no shitsu.
無名ファン
Kwan.
quality without thing この一番左ではその時間の問題と空間の問題とのはっきり分けて論じていると思います。でそれでうまくいかないとその対称性の破れっていうのはまた生じてくると。でパターンになってくるとその時間と空間っていう区別がなくなって全てはこう無名の質っていうものに変えていくと全いつ全
That probably gets, yeah, well over. Wow, it's 10:30. I should probably stop. Any other discussions or questions or ideas or?
So we can't get patterns in one project. You mean? If we suppose we start a project tomorrow, we cannot get the pattern on the first day.
We haven't been around long enough to have a knowledge what they are. In telecom, we have a few. How many of you know what a leaky bucket counter is?
Leaky bucket.
This is a really good example of time and space together. So, let's say you have some noise on a digital signaling line. And you can usually correct it. But if you have too much noise, the correction packets will take up all of the bandwidth and it will just crash. So what we have is we have a counter that counts the number of errors in the packets, and every time there's an error, we add one to the counter. And then there's a hole so that every second it leaks one counter. If this bucket overflows, something is wrong. Errors are coming very, very fast. Shut down the link, otherwise you will saturate the link and take down the system. So we have 20 or 30 of these in telecom. This is time and space together. This is a real pattern. Most of the patterns I have seen at PLOP here in Japan are not patterns. They're just a solution to a problem in a context.
データの伝送処理で誤ったデータが伝送されてきたときにそれを訂正するために訂正しようという信号を返していると溢れてしまう。そこにリーキーバケットっていうその水漏れがするバケツっていうのを設けてそこにこう信号が入ってきて正しい信号が出てくるんだけども間違った信号が出ていかないからこういずれバケツが溢れると溢れたら全部チャラにしてやり直すということをするとうまくいくんだと。でこれは時間の要素と空間の要素を両方とも含めて考えたパターンだということだと思います。日本のプロップでやってるのはこの時間と空間の要素が含まれてない、ストラクチャー構造のパターンであるということをおっしゃっていますと思います。
So, if you want to learn, there's a lot of things you can find on the web to read about this. And I mean, there's several ideas you should take away from tonight. One is, maybe some of you understood object-oriented programming and what it is for the first time tonight. And what you have been doing is class-oriented programming.
順々に行くんですよね、多分。
Maybe this will help you explore better what a pattern is and its relationship to time and to cosmology and to symmetry breaking. I mean, Alexander himself has written a lot about the relationship between patterns and spontaneous symmetry breaking. He worked pretty closely with a physicist at University of Texas at, I think it was Austin. Nikos Salangaros was the guy's name. And so you find a lot of physics in Alexander's writings. So, I mean, there's a lot more for you to pursue and study, because I think a lot of the things that we work with day to day, in terms of what is object orientation, what is a pattern, what is design, what is a working program, are extremely vulgar and very poor. So we're kind of where people were in the Middle Ages, trying to make gold out of straw. And we know better. I mean, all of this is known in the world. It's just that in our craft and in our practice, and because of academia and what academia teaches, that we're working at this very vulgar level of ignorance. There's some really powerful, unbelievably powerful stuff beyond this.
考え方がリーンなんですか。これがリーンっていうか、こういう構造なんですよね。こういうアーキテクチャをグループ、いわゆるこのストラクチャーとプレスされたアーキテクチャがあると、こう思ってあるというのがリーンの考え方。
But I think it's getting late, and some people probably want to go home to their families.
まあ一旦区切りとして。はい。
おっしゃったオブジェクト思考の皆さん今晩初めて分からないクラスいわゆるクラス思考ではないオブジェクト思考というのは何かっていう話が第1点で、第2点が何でしたっけ？パターンの話。対称性。
第2点の話をします。I'm sorry, what was that? So you have three takeaways?
The first point is that object orientation, the real meaning of object orientation.
Maybe.
Yeah.
Yeah. Second point is about symmetry breaking.
Yeah?
Yeah.
Well, but pattern?
About patterns.
Yeah,
I mean,
about
what is a pattern? And this integration of time and space that is based on centuries of insight and experience.
To get pattern needs long time?
Centuries.
Century?
I mean, telecom has been around for more than 100 years. So in these mature domains, we can start finding the patterns. I mean, we've been around long enough that we know what works.
今日明日の話しちゃうと。
Those fields are in the more academia.
Well, when we initially built the pattern community, we stayed away from academic tradition because what academia values was very different than what we valued. And it was a good idea. If you look at some of the research of people like Wolfgang Pree on meta patterns, or some of the work, I can't remember the name of the guy out of Israel, who did formalization of patterns. I mean, academics are always looking to do something novel. Patterns have nothing to do with novelty. They have nothing to do with formality. They have nothing to do with meta. And all of these are things that academia values. And so we tried to keep academia out of it for as long as we could. This was conscious, and we discussed this when we launched the pattern movement. And by now, of course, it's all over. The battle is lost.
アカデミックなアプローチとか形式的とかそういう手法を重視するんだけど、それではパターンにうまく扱えないと。パターンを作るには先ほど電信の例だとキ 100年ぐらいの歴史がある。そこから時間変わる話なんだと。そういう。
Before, just one thing before we end, and before I forget it, I think we should appreciate our hosts tonight. I mean, this is a wonderful space, and I want to appreciate their hospitality and a great talk, and just it's wonderful that companies like Loom are supporting the community here and making things like this possible. So. Thank you very much.
じゃあこの辺で。
そうです。